Hello, welcome to the OneClass channel. My name is Marlyn. I'm a second year student at the University of Waterloo studying chemical physics and math. Today I'm going to be working through some high school level and college level chemistry problems. Be sure to check out the links in the description if you're in need of any extra homework help or would like some one-on-one tutoring. Okay, so for our first question, we would like the full electron configuration for a ground state nitrogen atom. And so, to begin answering this question, we need to understand how to get the electron configuration. Ground state nitrogen. So the electron configuration is notation that displays sorry, just one moment. My apologies about that. Okay, so we need to understand what the electron configuration really displays, and it is notation that displays an atom's so it displays an atom slash ions slash molecules electron distribution in atomic or molecular orbitals. Okay, and so there are three main principles that govern how we're going to distribute these electrons inside of these orbitals. Three main rules is how we can think about them. And so first and foremost, we're going to have the Aufbau principle. And that one simply states that electrons occupy orbitals of lowest energy first. The second principle is going to be the Polyexclusion Principle. And that one simply states that no two electrons can have the same four quantum numbers. And so you can think of this as the address for the electron, and no two electrons can be basically at the same exact spot or occupying the same, occupying the same spot. And so what this usually will imply is that two electrons can occupy an orbital, but to avoid violating this exclusion principle, they will have opposite spins, so that their last quantum number is different. So they would have spin of 1/2 and spin of -1/2. Okay, and then the last one is Hund's rule. And that one just states that every orbital should be singly occupied before any is doubly occupied. And this is just to minimize the energy, because let's say we have 3 orbitals like this, and I begin by filling. So Hund's rule would dictate that I need to fill them all individually first before I come and I add another electron. And this is just to minimize the energy of the configuration of electrons, so that way we're building up kind of in the same way as the off-board principle. So all of these rules are just so that we can fill in a manner in which we get the lowest energy state, which is the ground state of the nitrogen atom. And so the majority of these principles can be executed if we follow Madelung's rule, which can be illustrated as such. Okay, and so how we're going to fill it is you always fill 1s first, and then 2s, and then 2p and 2s, followed by 3p and 4s, and then 3d, 4p, 5s, 5d, 5p, 4f, 5d, 5f. And so let's write that out. So it would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. Next up is 5s2, so I'm just filling this way, 4d10, 5p6, 4f14, 5d10, and then 5f14. So this is how you fill it. So depending on what atom we have and where it stops on the list, so for example, it has 4 electrons, I'd be stopping 1s2, 2s2, and that would be the configuration for the lowest, for the ground state of the atom. And so the great thing is that this is captured pretty well in the periodic table. So if we actually read along the periodic table, you'll get the same order that is dictated by Madelung's rule. And so we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 4f, I had failed to include the 6th row here. If we are supposed to be counting it properly. 6D, 6F. So let's just extend these. So that one stops there. This one looks like that. This one looks like that, and that one looks like that. And so we will have 5P6 indeed. And then 6S2, followed by the 4F14. 5D10, 6P6. Let's stop there because this would involve other things below it too. So just as I said, 3S2, 3P6, 4S2, 3D10, 4P6, 5S2, 4D10, 5P6, and then we have 6S2. We'll enter the lanthanides with 4F14, and then 5D10 here, and then 6P6, and so on and so forth. So you can either use Madeline's rule to fill it in, or you can use the periodic table itself. And so now let's figure out the electron configuration for nitrogen in specific. And so we're looking for nitrogen. If we just look at the periodic table and where it is, we can see that it has 7 electrons. And so if we were to follow Madeline's rule, we just count until we have 7 electrons. So we have 2, 4, and then this would enter 10 category. And so we're just going to subtract off the extra 3 electrons, and it should look like 1s2, 2s2, and then 2p3, not 6. That way they can add up to the 7 electrons. So if you count it down on the periodic table, 1s2, 2s2, and then 2p1, 2, 3. So 2p3 to get to nitrogen. If you wrote in the 6, it would be neon. And so that is going to be the electron configuration for ground state nitrogen. Okay, for our next question, we want to complete the electron configuration for aluminum. So similar to exactly how we did what we had before, we can just write in Madeline's rule again. And let's just check where aluminum is on the periodic table. And so we find it here. So we're expecting to go into the 3rd period, so it should be ending in 3p1 if we follow the periodic table. And so let's just complete Madeline's rule on this side. Okay, and we only have to complete until there. So we can expect 1s2, 2s2, 2p6, 3s2, 3p6 going on. And then let's figure out what it is for aluminum in specific. Aluminum has 13 electrons, so we know we will not be going past 2, 4, 10, 12, 18. And we said 13 electrons. So we're not going to be going past exactly here. So we were choosing to stop. And we know we only have 13. This is until 18. So we're going to be subtracting 5 from this one. And so that means that aluminum is going to be 1s2, 2s2, 2p6, 3s2, 3p1. If you follow the periodic table, 1s2, 2s2, 2p6, 3s2, 3p1. Exactly what we predicted here. Next up, you're given that the wavelength of radiation emitted when the outermost electron of aluminum falls from the 4s state. So from, let's say that this was in a state where this last electron was in the 4s orbital instead of the 3p state. So this is an excited state, and we want it to fall back down into this 3p is what that is describing. And so the energy that it releases when it falls back down from the energy level of 4s1 to 3p1 instead is going to be 395 nanometers worth of wavelength if we convert it from energy to wavelength. And so they want us to find the energy separation in joules between these two states. And so the equation for that is that the change in energy is going to be Hc over the wavelength. And so H is the constant of 6.26 by 10 to the negative 34 joules seconds multiplied by the speed of light. So let's actually write it down here so we can have a bit more space. 626 by 10 to the negative 34 joule seconds multiplied by 2.998, I believe, by 10 to the power of 8 meters per second. And then that is all going to be over our wavelength in meters so that we can have some unit consistency. So that is going to be 395 nanometers by 10 to the negative 9 to convert it back into meters. And then you can just check that the units all make sense. So this meters cancels this meters and the seconds cancel to give you an answer in joules. And so the energy separation in joules is going to be 5.03 by 10 to the power of negative 19 joules. And we can call this E1. Okay. For our next question, we now have the outermost electron in aluminum falls from the 3D state to the ground state. So similar to what we had before, let's say that that the last electron wasn't occupying 3p, instead it was occupying 3d. And from just the Marlyn rule, we can tell that this 3d orbital is going to be higher in energy than the 4s because it comes after it. And so we can already expect that the energy separation is going to be larger between this 3p and this 3d because the 3d is further away. And so we should expect a value above 5.03 by 10 to the negative 19. And so we're just gonna do the calculation where we have delta E is again going to be Hc over the wavelength. We have the same constants. All over 310 nanometers this time by 10 to the negative 9 to convert it back into meters. The units should cancel just as they did before. And we get a value of 6.41 times 10 to the negative 19 joules. So this is exactly what we expected. It's higher than the 5.03. And we're going to call this E2. Now for our next question, we want to calculate the energy separation between 3D and 4S. And so we have that this is the energy separation between 3P and 4S. And we have that this is the energy separation between 3P and 3D. So if we do a sketch, it's going to make sense how we can calculate the energy separation between 4S and 3D using these two values that we have. So let's go on and make that sketch. And so just according to what we have in the Marlyn rule, we know it's going to be 3P as the lowest one, and then 4S above it, and then 3D above both of them. So let's go ahead and include that in our sketch. We have 3P here, 4S, and then we have 3D. We know that the energy separation between 3P and 4S is going to be described by E1. So what we found in this first question. and that the energy separation between 3D and 3P is going to be described by E2. And so from this, we can clearly see that the energy separation between 3D and 4S is going to be described by E2 minus E1. And that is going to give us 6.41 by 10 to the negative 19 minus 5.03 by 10 to the negative 19. And when you put those in, you will get a value of 1.38 by 10 to the negative 19 as the separation between these two. If you don't understand how we got E2 minus E1, you can just quickly see here that E1 plus E3 is equal to E2. Isolate for E3. And you get E3 is equal to E2 minus E1, which is a formula we used here. And so from this, as we expected, 3D is higher in energy than 4S. You can predict that from the beginning of the question if you just use Madelung's rule or read through the periodic table as described before. Okay, for our next question, we want to describe molar mass. And so in the word, we can see the word molar. And so let's first go about describing what a mole is. And so a mole is the unit to measure the amount of particles and it is specifically known that 1 mole contains 6.022 by 10 to the power of 23 particles. And this is also known as Avogadro's constant, sorry. Okay, and so now the molar mass is defined as the mass of 1 mole of a substance. And so, of course, if you have 6.022 by 10 to the power of 23 particles, and you have a particle has a mass of A grams, then we're just going to multiply that A by 6.022 by 10 to the power of 23 in order to get the mass of 1 mole. And so despite the fact that yes, elements do tend to have isotopes, instead we just use their relative abundances on Earth in order to calculate a weighted average for the molar mass. And so a very, very good example, let's just write down the equation for molar mass is just equal to the summation of the number of types of an atom multiplied by the atomic mass of an atom. Of that atom. Okay, and so take the example of Ch3Cl. First off, you just want to note down the atomic masses. And so carbon is going to have an atomic mass of 12.107 U, which is 12.107 grams per mole. Hydrogen has an atomic mass of 1.008 U, and that is going to give us 1.008 grams per mole. And lastly, chlorine has an atomic mass of 45.4 453 grams per mole. And so using what we know here about molar mass, we can find that the molar mass of CH3Cl is going to be 12.107 times 1. So for the carbons, we have 1 carbon and each is 12.107 grams, plus 1.008 multiplied by 3. So 3 hydrogens and each one is 1.008 grams per mole, plus 45.453 times 1. So 1 chlorine and each is 45.453. And that is going to give us a final answer of 50.584 grams per mole for this example. And so that's just how you go about calculating the molar mass. Okay, next up we want to calculate the Lewis structure for H2CO. And so as usual, let's count our valence electrons. And so we're going to have 2 by 1 from the hydrogens, plus 1 by 4 because of the carbon, plus 1 by 6 because of the oxygen. And this is going to give us 12 electrons to distribute. We can go ahead and label all of these valence electrons. H2, CO. And so now let's go about drawing a skeleton structure. And so let's place the hydrogens around the carbon and then the oxygen on its own. Typically we like carbon as the central atom. It can make the most bonds. So in this scenario, it is our central atom. We know the hydrogens can only make 1 bond, and then let's go ahead and put 1 bond between these two and fill in our valence electrons. And let's see if, fill in our octets, and then let's see if we get 12. We have 6 from the oxygen, plus 2 from the carbon, plus 2 for 6 caught in bonds, so 3 by 2 in bonds. And that is going to give us 6 plus 2 plus 6, and that's 14 electrons. So we have an extra 2 electrons here that we don't need. And so the best way to fix this is going to be, let's put a double bond between these two here in order to get rid of 4 electrons and add an extra 2 because of the bond. And so again, let's count our valence electrons. We have 2, 4, 6, 8, 10, 12. Perfect. And all of the octets are full here. Oxygen has its 2, 4, 6, 8. Carbon has its 2, 4, 6, 8. And hydrogen likes 1. Let's check our formal charges. So on carbon, we are going to have 4 minus 8 over 2, which is going to give us 4 minus 4, which is 0. On the oxygen, we'll have 6 minus 4 over 2. That's going to give us 6 minus 6, which is again 0. And lastly, on our hydrogen, we are going to have 1 minus 0 minus 2 over 2. That's just going to be 1 minus 1, which is 0. And this is exactly what we had expected, to have a net formal charge of 0. And so our formal charges are happy and our valence electrons are happy too, which means that this is going to be our final answer. And so they would like one with dots and dashes and one with dots only. So if we have dots only, we'll have 2 electrons in the bond there, 2 electrons in the bond there, 4 electrons in the bond there, oxygen, and it's 4 valence electrons. So this would be the dot structure. Okay, next up we'd like a Lewis structure of CH3 NH2. And we can additionally quickly name this. This is a methyl group. And this is an amine, is what the ending tells us. So this is called methylamine, or amine, if you'd like to call it that. Is the name of this. Okay, and so let's count our valence electrons as usual. We'll have 4 from the carbon, plus 5 by 1 from the hydrogens, plus 5 from the nitrogen. And this is going to give us a total of 14 electrons. You can go ahead and label them just for clarity. C, there's H5, N. Okay, and then we start with our skeleton. Okay, and so let's start with one bond between everything and fill in any octets that are not yet full. Okay, and then let's just count through things. So we have 2, 4, 6, 8, 10, 12, 14. And so with this structure, we can see that everything's happy this way. Let's just redraw this so it's a bit clearer. So we'll have N attached to 2 hydrogens and then that. And so our valence electrons are all accounted for. Let's double check on our formal charges. For the carbon, we are going to have 4 minus 0 minus 8 over 2. This is just 4 minus 4, which is going to give us a 0. For all of the hydrogens, we are going to have 1 minus 0 minus 2 over 2. That's simply 1 minus 1, which is again going to give us 0. And lastly, on the nitrogen, we will have 5 minus 2 minus 6 over 2, which will just give us 5 minus 5, which will give us 0. So the formal charges all make sense. We have a net of 0 as expected, and our valence electrons are all accounted for, making this the final structure. On to our next question. We are asked for the Lewis structure of PBr3. And so let's begin by counting our valence electrons. And so for our valence electrons, we will have 5 from the phosphorus and 3 by 7 from the bromine. We can, as usual, name these phosphorus, Br3. And this will just give us 21 plus 5, which is 26 electrons to play with. The question said I can assign lone pairs and radical electrons where appropriate and admit atomic charges. From here we can see that this is an even number, so we're not going to have any radicals. And so there are no radical electrons. And so we'll just have lone pairs and bonding pairs. Let's go ahead and create our skeleton. We're going to have P in the middle, and then Br, Br, Br. If you'd like to know why I've chosen P as the central, we know that the central atom should be the one that can make the most bonds. We can calculate how many bonds each one of them can make. The bromine can make 8 minus the valence electron, so that's 8 minus 7, so each can make 1 bond. Meanwhile, the phosphorus can make 8 minus 5, so 3 bonds. And so it can make more bonds, so it should be the central. Next up, let's fill in our octet on the bromines. And then let's see if we have any electrons left to stick on the phosphorus. So we have 2, 4, 6 on each of the bromines. So 6 by 3 plus 2, 4, 6. And that is going to give us 24 electrons. So we have 2 more electrons that we can stick on the phosphorus like that. And so our valence electrons are all accounted for now. Let's double check on our formal charges. For the bromine, we'll have 7 minus 6 minus 2 over 2. So 7 minus 7, that's going to give us 0. On the phosphorus, we can have 5 minus 2 minus 6 over 2. That is going to give us 5 minus 5, and that is also going to be 0. So our formal charges make sense. We have a net charge of 0 as expected, and our valence electrons are all accounted for, meaning that this is going to be our final structure. Next up, we want the Lewis structure for Ethy. So C2H4, we can already tell from the name and from its general structure that it's going to be an alkene that have the general formula CnH2n. And so we can count the valence electrons as we usually do. We're going to have 2 by 4 plus 4 by 1. Go ahead and label these. This is going to be carbon. And this is going to be our hydrogens. And this is going to give us 8 plus 4. So we have 12 electrons to play with. Let's go ahead and write out our general structure. And of course, as usual, start with one bond between each. So this is made 3, which would leave 2 more valence electrons if we were to fill in their octets. And so let's count how many valence electrons this would imply. So we have 4 plus 2, 4, 6, 8, 10. And so this would imply 14 electrons, but we only have 12. And so we can fix this issue by getting rid of these 2 electrons and putting a double bond between them. Now let's count the valence electrons. We'll have 2, 4, 6, 8, 10, 12. So the valence electrons are all accounted for. And carbon is happy, it has its 4 bonds. Hydrogen is happy, it has its 1 bond. Let's double check on our formal charges. On the carbon, we're going to have 4 minus 0 minus 8 over 2. And that's simply 4 minus 4, which is 0. On the hydrogens, we're going to have 1 minus 0 minus 2 over 2. That's simply 1 minus 1, which is again 0. Our formal charges make sense. We expected a net charge of 0 according to the question. And all of our octets are happy, and the valence electrons are all sorted out. So this is going to be our Lewis structure for Ethy. Now, based on this structure, we want to predict the HCH bond angle. And so let's figure out the molecular geometry for this molecule. So this carbon, let's use some red. This carbon is 1, 2, 3. So it has 3 bonding pairs. If it's a double bond, we're going to count it as 1 according to the rules. And so this is going to be sp2 hybridized. And so is this one, sp2 hybridized. So it has 3 axial things attached to it. And so what that means when we go back to our VSEPR chart is 3. So it's going to be an angle of 120 between each trigonal planar. And so we've already made this sketch kind of look like it's trigonal planar. We can resketch it. And that usually happens if you're good with your VSEPR. And so we have H, 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 H. So you can see the shape here. And this angle is going to be 120 degrees. This is going to be 120. And this is going to be 122. Similar on this side. Which means that the HCH bond angle is going to be 120 degrees. And then we want to sketch the molecule showing the predicted bond angles, which we have already done here. And that is it for this question. So POCl3 has the skeleton structure depicted here. What is the Lewis structure for POCl3 following the octet rule? And what are the formal charges that causes on all of the atoms? And what is the Lewis structure for POCl3 in which all formal charges are 0? So let's go about that. So as usual, we're going to want to start with our valence electrons. We're going to have 5 from the phosphorus by 1 because there's only 1, 6 by 1 because of the oxygen, and 7 by 3 because of the chlorine. You can go ahead and label this. This is POCl3. And this is actually going to give us 21 plus 11, so 32 electrons. So we have 32 electrons to play with. From this, we can quickly figure out which one is the central atom. It can make the most bonds. For phosphorus, that's going to be 8 minus 5, so it can make 3 bonds optimally. Oxygen, it can make 8 minus 6, so 2 bonds optimally. Chlorine, it can make 8 minus 7, so 1 bond optimally. And so we're going to have P in the middle. We have 3 Cls, and we have 1 O. Let's start with 1 bond on each of them and fill in our octets. And this is what we're given as the Lewis structure following the octet rule. And so we have 2, 4, 6 by 4 plus 8. That's going to give us 24 plus 8 electrons, and that is the 32 electrons that we have. So this Lewis structure does work. Now let's double check on the formal charges to see if it's the lowest energy Lewis structure for this molecule. And so on our formal charges for the phosphorus, we are going to have 5 minus 0 minus 8 over 2. That's going to be 5 minus 4, giving us a positive 1. So the phosphorus is going to have a positive charge. Let's double check on the oxygens. We'll have 6 minus 6 minus 2 over 2. That's going to give us 6 minus 7, giving us a negative 1. And now let's see the chlorine. We're going to have 7 minus 6 minus 2 over 2. That's going to give us 7 minus 7, which is 0. And so the formal charges make sense. The structure given in the question doesn't have any charges. These two charges would cancel, yielding a net charge of 0. But from this, we can also tell that this is not the lowest energy structure for the molecule, because in order for it to be the lowest energy structure, we'd like to neutralize these charges somehow using different electron arrangements, so we can bring the formal charges on each of them to the lowest value that they can be while still maintaining our valence electrons. And so we can do that if we make the decision to cancel out one pair of electrons here and actually cause a double bond. Now, this would imply that phosphorus has more than the usual 8 for an octet, but this is going to be allowed because phosphorus can form an overfilled octet using the fact that it has d orbitals somewhere close to it, according to the periodic table. If we just check here quickly. No, it technically cannot, but it's what is asked for in the question. For what is the Lewis structure if all the formal charges are 0, and this is the structure that would allow all those formal charges to be 0. So it's just a theorized structure. And so in this case, let's just ensure all of those formal charges are 0, because that is what is asked for. And so on the phosphorus, we're going to have 5 minus 0 minus 10 over 2. And that is going to give us 5 minus 5, which is 0. On the oxygen, we're going to have 6 minus 4 minus 4 over 2. And that's going to be 6 minus 6, which is 0. And on the chlorine, we are going to have 7 minus 6 minus 2 over 2, which is just 7 minus 7, which is 0. Okay, and so if you want to, so all of this makes sense. We have formal charges of 0, and this is the structure that would allow for it. So in this state, the phosphorus is exhibiting an expanded octet, which means more than 8 electrons. Okay, next up, we would like to draw out some Lewis structures. So we start with Hco3. As usual, count our valence electrons. We'll have 2 by 1 because of the hydrogen, plus 1 by 4, plus 3 by 6. And this is going to give us 24 electrons. To think about, we can label them H2, C, O3. And so now let's just draw out our skeleton structure. We already know carbon is the central atom because it can make the most bonds, 4. But we are actually going to place the carbon surrounded by oxygen and then the hydrogen. And that is just based on the fact that hydrogen can only make one bond, so that makes the most sense, so that it can make one bond here. And then let's start with one bond on each. And so this way, let's fill in the octets of each of them. And let's see if that adds up to our 24. And so we're going to have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So clearly here we have too many electrons. And so let's figure out where we can change the arrangement in order to make them 24. Now it's tempting to do it on any of the oxygens, but we're actually going to make use of the fact that we know how many bonds oxygen would like to optimally form to minimize its charge, and that's 2. We can see that this oxygen already has its 2, so it has a formal charge of 0 already, and so does this one. And so changing them won't benefit us because it's going to mess up the charge, and that would mean that it isn't the best structure that we can present. So the best oxygen to change is actually this top one to give it the 2 bonds that it would like to have, leaving it with a formal charge of 0 like the rest. And so let's see if we have our 24, 2, 4, 6, 8, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So our valence electrons are all accounted for. Now let's check on our formal charge. On each of the oxygens, we'll have 6 minus 4 minus 4 over 2. And that's going to give us 6 minus 6, which is 0. On all of the hydrogens, we have 1 minus 0 minus 2 over 2. That's 1 minus 1, which is 0. And lastly, on the 1 carbon, we have 4 minus 0 minus 8 over 2, giving us 4 minus 4, which is 0. This is all expected. We had a net formal charge of 0. And so our valence electrons are all accounted for, and our charges are all accounted for. So this is the correct Lewis structure. Next, we're asked for any equivalent resonance structures. And so we need to think about what resonance structures mean. And so resonance structures are just a set of 2 or more Lewis structures that collectively describe the electron bonding of a single polyatomic species. By including bonds and fractional charges, they describe delocalized electrons in double bonds and lone pairs that a single Lewis formula cannot describe on its own. And so when we want more resonance structures, we need to figure out, can we move any of the electrons in double bonds or lone pair electrons to get another similar looking Lewis structure? In this case, no, we can't, because if we decide to move the electrons here, let's say to go back into a lone pair, we know that that would mess up the charges. Same thing here. If we decide to move these lone pairs on their own, it would mess up the charges and make them non-zero. And so this only has one equivalent resonance structure. For the following ones, that may not be the case. And so let's move on to our next one, which is Hco3 minus. Let's count our valence electrons. We're going to have 1 plus 1 by 4 plus 3 by 6 plus the additional 1 because of the charge. And that is going to give us 2 plus 4 plus 18, which just happens to be exactly what we have here. So we're still going to have 24 electrons to play with. Again, let's draw our skeleton. But remember, we only have 1 H, so we can put that on either side. And so let's start by 1 bond on each and fill in our valence electrons and see if we have our 24. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So clearly, again, we have too many electrons. So let's see what we can do to bring the electrons down to 24. So we would optimally like to move 2 electrons into another additional bonding pair to do that. This oxygen has already made its optimal 2 bonds, which means we're going to be playing with one of these 2. And so let's play with the one on the top by getting rid of those 2 electrons and adding a bonding pair like that. And so this way we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So our valence electrons are now all taken care of this way. Next up, we need to check on our formal charges. We should be expecting a net formal charge of -1 because of this negative up here. So on the oxygens, we're going to have these 2 cases, which will label 1, in this case, which will label 2. So on the case 1s, we're going to have 6 minus 2, 4. So they both have 4 lone pairs, minus 2, 4, 2, 4. So they both have 4 electrons in bonding pairs. And that's going to give us 6 minus 6. So they will have a charge of 0. Let's check in on our hydrogen. We're going to have 1 minus 2 over 2, which is 1 minus 1, so 0, 2. On our carbon, we're going to have 4 minus 0 minus 8 over 2. 4 minus 4, going to give us 0. Let's check in on this second case, oxygen, where you have 6 valence electrons because it's oxygen. Minus, we have 6 lone pairs, minus 2 electrons in the bonding pair. So we're going to have 6 minus 7, and that's going to give us -1. These formal charges make sense because we expected a net formal charge of -1, which is what we do have. So the negative is going to be there. Okay, so this is going to be our lowest structure, right? And now we want to figure out if there are any resonance structures for that. We can do that by seeing if we can move any lone pairs or bonding pairs, if it's a double bond, in a way that doesn't mess with the valence electrons and doesn't mess with the net formal charge. And indeed we can, if we decide to actually instead have this one having the 8 electrons and this one having the double bond instead. And that way we would move the charge from there to here, and this would have the charge of 0. And so now let's write them out as separate things. So we will have C with the double bond at the top, attached to the OH and attached to the O. And then the minus would be on this one. Or alternatively, we can have a double bond here instead and the minus on this one. So this one remains OH. And this one gains the double bond to have that, and the minus on this other one. We can't move the double bond to this because that would make this one negative, this one -2, and then this one will be positive. And so we'd like to minimize the charges on the individual atoms each time. In that case, yes, the net charge would be correct, but you wouldn't have minimized the charges on the individual atoms. And so we only have 2 equivalent structures. Okay, and then last up we have Hco3 Minus. Let's count our valence electrons. We're going to have 4 plus 3 by 6 plus 2, and that is again going to give us our 24 electrons to play with. And so now let's write out our structure. Okay, and then let's start with single bonds on each and filling in the octets of the oxygens. Okay, and then let's see if that all makes sense. We have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Let me just make sure I got that right. 6 by 3 plus 6 by 3. Sorry, 2 by 3. 3 by 2 for the bonding electrons. That's going to give us 18 plus 6, which will give us indeed 24 electrons as counted out. But, so yes, this is all correct so far. Let's check if this is the version that would minimize our formal charges on each. And so on each of the oxygens, we're going to have 6 minus 6 minus 2 over 2. And so that is going to give us a -1 charge on all of them. So they all have minus charges. And then let's check on the carbon. If we have carbon with a full octet, which should be optimized, then we'd have 26 electrons, which would break that because the valence electrons would be too many. And if we have carbon just like that, then we're going to have 4 minus 0 minus 6 over 2, which would give us a +1 here. And so in this case, we have two charges that we can neutralize with each other. And so this is obviously not the best structure because you haven't minimized the individual formal charges. And so let's go about doing that by adding a double bond. And so now let's see what we have. We have this oxygen with a formal charge of 0, this carbon with a formal charge of 0, and your 2 minus charges. So that all makes sense. We had a 2 minus in the question, and we've achieved it, and the valence electrons all check out. And so now we want to see if we can come up with any resonance structures for this, and indeed we can by moving this double bond around. And so we'd have 3 structures. We'd have what we've drawn. Additionally, we could have this double bond here instead, and this one with the full octet. And so we'd have and so the 2 minus charges would be down here. And lastly, we have if the double bond was here instead. And so you'd have the 2 minus charges here. And so these would be all of our resonance structures with a total charge of -2. And that's going to be your final answer. So you have 3 equivalent structures. And those are your final answers. Okay, next up, we're looking at conjugate acids and bases. So we just need to remember that according to Bronsted-Lowry acid-base theory, we have acids as proton donors and bases as proton acceptors. And so if we write out an equation for that, that means Ha plus B minus is going to give us A minus plus HB. All of this is an aqueous solution. And if you go ahead and label these, this would be our acid and its conjugate base. This would be our base and its conjugate acid. If we write out the base version of this equation, we would have B minus plus H2O to get you HB plus OH minus. Again, label them. This would be your base. Water would be acting as your acid. And this would be your conjugate acid and your conjugate base. Okay, and so if we write out the same equations for what we've been given, we can identify what the conjugate base is going to be and what the conjugate acid is going to be. And so, since we're looking for the conjugate base of HSO4 minus, let's write out this equation for it. So we have HSO4 minus plus a base that we're just going to label in the same way, so B minus, is going to give me SO4 2 minus plus HB. And so since this is my acid, this is going to be my conjugate base. And so the conjugate base of HSO4 is going to be the sulfate ion. So let's go ahead and write that out. Okay, and now let's look for the conjugate acid of HSO4. So we're going to be using this equation. And so we'll have, in this case, HSO4 minus is acting as our base. So we have HSO4 minus plus H2O to give us H2SO4 plus OH minus. So this would mean that because this is our base, this is going to be our conjugate acid. And so the conjugate acid of HSO4 minus is going to be sulfuric acid. And that's it. Okay, next up, we're looking for the Lewis structure for the following. And so we have BF4 minus is our first one. As usual, we're going to count the valence electrons. We will have 3 from the boron, plus 4 by 7 from the fluorines, plus 1 because of charge. Let's go ahead and label these. So boron, 4 minus charge, and that's just going to give us 28 plus 4, so 32 electrons to take care of. Let's start with our skeleton structure. We know boron is going to be the central atom because 8 minus 3 is equal to 5, and that is going to be greater than 8 minus 7, which is equal to 1. And so boron can make the most bonds in this scenario. And so let's start with our structure and single bonds between each, and fill in our octets for each of the fluorines. And see if all of the electrons make sense for our valence. And so we have 6 by 4 plus 8, which is just going to give us 24 plus 8, and that will give us our 32 electrons. So all of our valence electrons make sense. Let's double check on our formal charges. We expect a net formal charge of -1. For each of the fluorines, we're going to have 7 minus 6 minus 2 over 2. So formal charges, this is for fluorine, and that's going to just be equal to 7 minus 7, which is 0. For the boron, we're going to have 3 minus 0 minus 8 over 2. That's going to give us 3 minus 4, which is -1. So we're going to have a negative charge on the boron. Does that make sense? It gives a net formal charge of -1, so yes it does, meaning that this is going to be our final structure. Valence electrons are taken care of, formal charge is taken care of. On to the next one. We have Cl2O. Let's count our valence electrons. We are going to have 2 by 7 because of the chlorine, plus 6. And that's just going to give us 14 plus 6, which is 20 electrons to take care of. We can label these as Cl2O. And so let's start with our structure like this. So Cl, oxygen clearly deserves to be in the middle because 8 minus 6 is 2, and 8 minus 7 is equal to 1, and 2 is greater than 1. So oxygen can make the most bonds in this case. Let's start with a single bond between each and filling in the octets. And see if that matches our valence electrons. We have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So our valence electrons are all taken care of. Let's double check on our formal charge. On the oxygen, we're going to have 6 minus 4 minus 4 over 2. That's just 6 minus 6, giving us 0. On the chlorine, we're going to have 7 minus 6 minus 2 over 2 for both of them, which is 7 minus 7, giving us 0. This makes sense. We expected a net formal charge of 0, which we've gotten. And the valence electrons are all taken care of. So this is our final structure. On to the next question. We have NH2OH. Again, count the valence electrons first. We're going to have 5 plus 3 by 1 plus 6. This is going to give us 8 plus 6. which is just 14 electrons. We can label these. This is N, H3O. Let's figure out what our central atom is going to be. For nitrogen, it can make 8 minus 5, so 3 bonds. Oxygen, it can make 8 minus 6, so 2. Hydrogen, it can make 8 minus 1, so 7. But typically, hydrogen can't be the central atom because it can only make 1 bond, actually. So nitrogen is clearly going to be our central. We can place those around it. And that's the OH. Let's add 1 bond in between all of them. Sorry, we have 3 hydrogens, not 4. Let me just restart that so you can see how it got there. We said nitrogen is clearly the middle. Let's put 2 hydrogens around it. And the oxygen, we know hydrogen can make optimally 3 bonds. So we have 3 things around it already. So let's put the H on the other side of the oxygen. Start by adding 1 bond in between each and filling in the octets. And then let's see if we have enough electrons. So we have 2, 4, 6, 8, 10, 12, 14. So yes, all of these are taken care of. Let's double check on our formal charge. For the nitrogen, you're going to have 5 minus 2 minus 3 over 2. Sorry, 6 over 2. Because each of these count as 2 electrons in each bonding pair. That's going to give us 5 minus 5, which is 0. Oxygen, we are going to have 6 minus 4 minus 4 over 2. 6 minus 6, which is 0. Hydrogen, we are going to have 1 minus 0 minus 2 over 2 for each of them. That's simply 1 minus 1, which is 0. Formal charges make sense. You expected a net formal charge of 0. Valence electrons are all taken care of, meaning that this is our final Lewis structure. And then lastly, we have CH2, Cl2. So let's just rewrite that in our C2, H2, Cl2. Let's count our valence electrons. You're going to have 2 by 4 plus 2 by 1 plus 2 by 7. That's going to give us 8 plus 2 plus 14. So that is 24 electrons to take care of. We can label these. This is the C2, H2, Cl2. And so clearly here we're going to have C. Let's put the H on one of them and the Cl on the other. Let's start with a single bond between all of them. And filling in our valence electrons, our octets. See if that adds up to 24. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So clearly we have too many electrons here. Now we need to figure out the best lone pair that we can move into a bonding pair. If we move the Cl's ones, so let's say we decide to make a double bond here, that means Cl is going to have a formal charge of something other than 0, and the carbon is going to be fine. But it's going to mess up our formal charge more than if we instead decided to make this double bond here, because carbon can still make 1 more bond. And so let's leave it like that and see. So now we'll have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So now all of our electrons are taken care of and everybody's octets are filled. Let's double check on our formal charge. For the hydrogen, they're going to have 1 minus 0 minus 2 over 2 for each of them. And that's going to give us 1 minus 1, which is 0. For the carbons, we're going to have 4 minus 0 minus 8 over 2. That's 4 minus 4, which is going to give us 0. And lastly, for chlorine, we are going to have 7 minus 6 minus 2 over 2 for each of them. So 7 minus 7, and that is going to give us 0, 2. And so these formal charges make sense. We expected a net formal charge of 0, which is what we have. And so this is going to be our final structure. If we'd like to be a little more correct, we can write it in a way where its geometry would be reflected. And so we can write it out like that. And that is going to be your final answer with the octet on the chlorines. Next up, we want to figure out which molecule is polar. So first we need to, in order to determine polarity, we need to find the Lewis structure, and from there we find the molecular / electronic geometry, and then we figure out whether it's polar by examining the symmetry of the dipole moments and seeing if they all cancel out to 0 or non-zero, in which case it would be polar. So if we start with C2H4, we can already tell from its general name that it's going to be an alkene because of the CnH2n general formula. If you'd like to count the valence electrons, it's going to be 4 plus 8, so we have 12 electrons to care about. Cc, let's put a H around both of them. If we start with 1 on each, it would leave us with 2 extra electrons on the carbons, and we know carbon is optimized for 4 bonds. Let's just give it that by adding a double bond in between them. See if that adds up to our 12, 2, 4, 6, 8, 10, 12. So yes, this is our Lewis structure. And next up, we need to find the geometry by finding the hybridization of each carbon. This is going to be sp2, and this is also sp2. That's because it has 3 things attached to it. So you have 1, 2, 3. This double bond, we're going to count it as 1. And so because of that, it is going to be trigonal planar. And so it should have a shape like that on each of the carbons. And so if you actually wrote that out for each of the carbons, then you'd get something like that. And then just imagine taking it from this orientation and straightening it out like this. And instead now we get something that looks like that. Okay, and then now let's write out the dipoles to see if they cancel. So we're going to have an angle of 120 because of the fact that it's trigonal planar. This dipole is going to come this way. Okay, and so these two are going to cancel and these two are going to cancel. So due to the symmetry, the dipoles will cancel, meaning that it'll be non-polar. Let's check out our second one. We have CS2. If you want to check out our valence electrons, that would mean that we have 4 plus 6 by 2. So 12 plus 4, so 16 electrons to play with. Let's put carbon as our central because it can make the most bonds, S and S. Now if you do it this way and fill in the remaining electrons for each octet, we'd have more than 16 because we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. And so the best bet would be to give carbon its 4 bonds by creating 2 double bonds. And this way we can see carbon has its octet filled, each sulfur has its octet filled. Let's check if we have 16, 2, 4, 6, 8, 10, 12, 14, 16. So our valence electrons are covered. Now let's see if the formal charges are covered too. For the sulfur, we're going to have 6 minus 4 over 2. 6 minus 6, 0. For the carbon, we're going to have 4 minus 0 minus 8 over 2. 4 minus 4, 0, 2. So the formal charges also check out. And so now let's try and find the geometry. We have a central atom attached to 2. And so if you go to the Vesper, it has 2, and so it's just going to be linear. And so it should have an angle of 180 here. Next up, let's check in on our, so this is a correct Lewis structure, is what we've just determined. Now I want to find the geometry. We found that it's linear, so we see if the dipoles will cancel again. This has a dipole pointing out like this. This has a dipole pointing out like that, which means that these two will cancel exactly because the 2 dipoles are equal due to the difference in electronegativity between carbon and sulfur. And so this is going to be due to the symmetry again. This means that dipoles cancel, meaning it is non-polar too. And that's your final answer for that one. Next up, we have C6H6. This one you can easily determine that it's benzene, so let's just write it out. This has 3, so it's just going to need one more. All of them are like that. And so you have 6 hydrogen, 6 carbon. You can double check on your valence electrons. We should have 4 by 6 plus 4. 24 plus 4, 28. Let's just double check that we do have that. Let's just not forget to count these as well as bonds. And so we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Sorry, let's start again. 2, 4, 6, 8, 10, 12, 14, 16. Sorry, I always forget about the hydrogens. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28. And so we see all of our electrons are accounted for. And so this is going to be our Lewis structure. And then let's find out the molecular geometry. It's benzene, so it's just going to be a planar ring. And if you actually draw all of the dipoles, they should all cancel. And so this cancels this, this cancels this, this cancels this. And so due to the symmetry again, dipoles cancel. And so this is also non-polar. On to our second last one. We have SO2. Our valence electrons are going to be 6 plus T by 6. So that's just 3 by 6. So we have 18 electrons. We're going to put sulfur in the middle and the 2 oxygens. Start with single bonds. Fill in all of the octets. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Too many electrons. And we also know oxygen likes to make 2 bonds. So let's just give both of them their 2 bonds. By creating a double bond here, double bond here. Okay, now let's see. 2, 4, 6, 8, 10, 12, 14, 16. And so we're going to have an extra 2 electrons left over for the sulfur. And so now let's see how many the formal charges, what they'll look like. For the oxygens, we're going to have 6 minus 4 over 2. Again, 6 minus 6, 0. For the sulfur, we're going to have 6 minus 8 over 2 minus 2. And that's going to give us 6 minus 4 minus 2, which is also 0. So the formal charges make sense and the valence electrons are all accounted for. We can also see here that the sulfur has an expanded octet. Now let's figure out the geometry. We have 3 groups attached to it, the oxygen, the second oxygen, and the lone pair. And so if we just check this out here, we have 3, but 1 is a lone pair, and so it's actually going to be bent. And so it should look like this. And so because the lone pair will repel a bit more than the electrons in these, this angle is going to be a little under 120 degrees, because this angle is going to be, of course, over 120. Sorry. Because this angle is over 120, and so is this one. It's also over 120. So this one is less than 120. And so this is what it's going to look like. Now let's see if the dipole moments will cancel. We have a dipole moment that is up towards the lone pair. Sulfur is pointing down towards the two oxygens. And so we see that indeed this can be written as this, and this can be written as this and this. So these two will cancel because the two are equal. And you're actually going to get a dipole moment. One is pointing up and the other is pointing down. But these two dipole moments will not be equal because the dipoles created by the oxygens is not equal to the dipole created by the lone pair. So because of the lack of symmetry in this case, dipoles do not cancel. And that makes it polar. So this is the only polar one that we've stumbled across. And lastly, we have CF4. Let's just double check that that is not going to be polar. We're going to have 4 by 7 plus 4, so 28 plus 4, which is going to give us 32 electrons. Carbon is going to be in the middle. Let's start with a single bond for each, and then the fluorines. Fill in your octets. And so we have 2, 4, 6, 8 on each of these, so 8 by 4, that is going to give us our 32. So our valence electrons all check out. Let's double check our formal charges. On each of the fluorines, we're going to get 7 minus 6 minus 2 over 2. That's just 7 minus 7, giving us 0. On the carbon, we are going to get 4 minus 0 minus 8 over 2, which is just 4 minus 4. Again, giving us 0. This is exactly what we expected, a net formal charge of 0. So this is our Lewis structure. Now let's figure out the geometry. And so this is going to be sp3 hybridized. And so let's just go to our chart. And we see it has 4 groups and they're all identical. So it's going to be tetrahedral. And if we draw out on what that looks like, it's a bit like a tripod. Okay, and so what's actually going to happen is that you will have this dipole moment going that way. This one, since it's like a tripod, let's actually draw it on the side so that we can get a bit of a better feel for the geometry. This one is coming out, this one's coming out, and this one's coming out. And so what's going to happen is these 3 are going to cancel each other out in the x, so in the horizontal plane, and it's actually just going to leave a vertical dipole moment. And then what is going to be left is for it to cancel out with this one that is going up, and so the 2 will cancel out too, leaving no dipole moment. So with this one, due to symmetry, it'll be non-polar. And so from everything we find that the only polar one is going to be SO2. So D is going to be your correct answer. Okay, next up, we want the Lewis structure for CF2CCl2. A good way to quickly think about this one is, so we have C2F2Cl2. Let's say we consider the halogens hydrogen, then you'd have C2H4. And that, of course, is the general structure of an alkene. And so we can expect this to be an alkene with the hydrogen substituted for other things. And so this would be the very, very quick way to get the answer. If you want to go through the long process, you count your valence electrons. So we're going to have 2 by 4, 8, plus 2 by 7, 14, plus 2 by 7, 14. That is going to give us 28 plus 8, so we have 36 electrons to take care of. Just start with your skeleton. And one bond between each. Fill in the octets for your halogens. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36. So yes, electrons do make sense in this case, but we need to remember that carbon would need a filled octet too. Carbon likes to make 4 bonds, and so in this scenario, again, let's count out our valence electrons, and we have we have technically 8 by 4. So 8 by 4 plus 2, 4 plus 2. And that is going to give us 32 plus 4 plus 2, which is 38 electrons. So here we have too many electrons. And so we need to drop them down by moving some of the lone pairs into bonding pairs. So it would be tempting to do it on any of them, but we know halogens like to make 1 bond. All of them have already made their 1 bond. Carbon likes to make 4 bonds. Each of the carbons have only made 3 bonds. And so let's just make both carbons happy by giving them both the 4 bonds by creating a double bond between them. Now we double check our valence electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36. So our valence electrons are all taken care of. Let's double check on our formal charge. Cl is going to have 7 minus 6 minus 2 over 2 for both of them. This is going to give us 0. Fluorine is going to look the exact same, 7 minus 6 minus 2 over 2, 0. And lastly, the carbons are going to be 4 minus 0 minus 8 over 2. And that is also going to give us 0. This all makes sense. We expected a net formal charge of 0, so this is going to be our final structure here. Valence electrons are taken care of, formal charge is taken care of. Okay, next up, we want to see which of the structures obey the octet rule. This can easily be done. Let's just count the electrons around each of them. And so for our case 1, we have 2, 4, 6, 8, 10 electrons. So clearly phosphorus is exhibiting an expanded octet here, not obeying the octet rule. For this one, sorry, let me just write that out so it's a bit clearer. We have that. And so if you just count all of those, this is going to be 2 electrons, another 2, so 2, 4, 6, 8, 10. And so this has 10 electrons around it, which is not equal to the 8 in an octet, so that is not obeying the octet rule. Next up, we have this. I'm not really drawing out what's on the F's because I don't care about that when I'm counting if the central atom is obeying the octet rule. I care about the electrons around the central atom. And so I have 2, let's count them. I have 2, 4, 6, 8, 10, 12. So I have 12, which is clearly over the 8. And so not obeying octet rule. Next up, we have Cl that looks practically the exact same as our first example. And so I can already tell it technically would not be following the octet rule. And so let's count them out. 2, 4, 6, 8, 10. So I have 10, which is not equal to the 8 needed for an octet. So this is not obeying the octet rule either. And now lastly, let's check our last one. And so here I have 2, 4, 6, 8. So I do have 8 8 electrons around it, which means that it is following the octet rule. So the correct answer is Alf4 minus is the only one obeying the octet rule. And that's going to be your final answer. Okay, next up, I would like to draw the Lewis structures for I2 and N2. So let's start with I2. That should have 7 by 2, so 14 electrons. We already know halogens like to make one bond, so let's start with just the one bond around each. And let's see if all of our valence electrons are satisfied. 2, 4, 6, 8, 10, 12, 14. Octets are all filled. Lastly, let's double check on our formal charges. We have, for the I, it's going to be 7 minus 6 minus 2 over 2 for both of them, giving us 0. And we expected a net charge of 0. So this is going to be our final structure for this one. N2, we are going to have 2 by 5. And so that is going to be 10 electrons to play with. If we start with just a single bond and fill in both octets, we're going to have 2, 4, 6, 8, 10, 12, 14. Clearly too many electrons. So let's sort that out by moving 4 of them into a double bond. Now that gives us 2, 4, 6, 8, 10, 12. So again, I have too many electrons. So I'm going to continue to do that. And now let's see, we have 2, 4, 6, 8, 10. So the 10 electrons are now taken care of. Let's check our formal charge. For each of the nitrogens, we are going to have 5 minus 2 minus 6 over 2. And that is also going to give us 0. So the formal charge is also taken care of. We expected a net of 0. And so this is going to be our final structure. Then I want to describe the bonding as single, double, or triple covalent bond. This one has a single bond between it. So the answer is single on this one. And this one has 3 bonds between it. So the answer is going to be triple. So it's a triple covalent bond and a single covalent bond for the first one, and triple for the second one. Okay, next up, I would like the Lewis structures for BrO2 minus and indicate the formal charges on both before we begin answering the questions. So we have BrO2 minus. Sorry, I'm trying to, yeah. So it is BrO2 minus. And so let's count our valence electrons. We're going to have 2 by 6 plus 7 plus 1. So 12 plus 8. So we have 20 electrons to play with. And so let's start with Br attached to 2 electrons. Sorry, 2 oxygens. Yep. And let's fill in both octets. Here we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. right? And so now so the electrons are all taken care of. Let's check in on our formal charges. On each of the oxygens, I'm going to have 6 minus 2 over 2. That's going to give me -1. On the bromine, I'm going to have 7 minus 4 over 2. And it's going to give me 7 minus 6. So this is going to be a +1 on the bromine. So let's just write that all out. And here we can see that we can actually make the individual formal charges, we can reduce them if we get rid of one negative and one positive. And the best way for us to do that would be for us to add a double bond on one of them. And so that would cancel out those electrons. And so let's double check we still have our 20. So 2, 4, 6, 8, 10, 12, 14, 16, 18. Sorry. And then let's add the last 2 on our bromine. So it can look like that. And so we have a double bond on one side. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. 20 electrons are taken care of. Our formal charges, this one will have a formal charge of 0 once you calculate it. Bromine will become 7 minus 4 minus 6 over 2. So it's going to become 0, 2, leaving the 1 minus. And so formal charges are now taken care of. So our formal charge will be taken care of, and our valence electrons will be taken care of. Okay, and so this is going to be our final structure. And then now let's see what else they ask for. Indicate the number of valence electrons. Draw the Lewis structure, sorry. So now we need to find any resonance structures for this. This can easily be done. We can decide to have the double bond here instead of here. So our resonance structures are going to look like this. Or this. So the minus can be here, or the minus can be here. Our 2 resonance structures. Okay, now indicate total number of valence electrons. We've indicated that. Describe the preferred Lewis structure. How many resonance structures we have? We have 2 as we found. And what is the shape of the ion? And so to find the shape of the ion, let's find how many pairs are attached to the bromine. We have 1, 2, 3, 4 groups attached to it. So we can expect a molecular geometry of tetrahedral. Now let's double check in on our electron geometry. We have 2 lone pairs and 2 bonding pairs. And so what that means is that if you come to the chart, it'll be bent. And so that's it for that. And so now let's come to the name of the ion. And the name of the ion is going to be the bromide ion. And that's the final answer for that one. Okay. And those are all of the questions I have for you today. I hope you enjoyed today's Q&A. If you'd like to be notified of when we post next, be sure to hit the subscribe button and the bell next to it so you get the notification when we do post. If you'd like to post questions of your own so that they can be answered on live stream, be sure to check out the links in the description for the OneClass page. This has been Marlyn from OneClass, and I hope to see you next time.